inviting me here. It's nice to be in Novita in Stockholm for the first time. It's not the first time I'm in Novita, and it's not the first time I'm in Stockholm, but it's the first time I'm in Novita in Stockholm. And this is very nice to see. I guess I should apologize for a few things here in the beginning. First of all, well, we all know that we are not in Santiago, and it's not the 7th of April, but due to some technical incompatibility issues, I was not able to change this part without destroying lots of other things in my slides. So, but we all know where we are and the date, so hopefully this is also important. And second, I would like to kind of apologize for giving a talk essentially about classical physics in a meeting that is supposed to be about quantum phenomena. I hope that you will get some motivation to why this could be relevant to some things that at least some people here in the audience have been studying. Essentially, there is some quite close analogy between the study of nonlinear waveguide arrays and the bosonic systems and optical lattices. I will mention a little bit about this later. But essentially, I will talk about purely classical physics here. So this work essentially was done during quite some time. It started up already in 2006 when I was visiting the group of Yuri Kirchner in Canberra. Then we were working on this for a couple of years, and in the end it was published last year in PRE. And during that time I also, as Egor said, I'm mainly working in Linköping University. During this time I was also spending some time in the University of Kalmar, it's some part of Sweden. What I'm going to talk about here is essentially some applications of some nonlinear dynamical methods, ideas, and how we can use these ideas to describe particular kinds of nonlinear localized modes in two-dimensional periodic structures. And essentially, well, the term here, discrete reduced symmetry solitons, second band vortices, I will explain soon what we mean with these things. And as a two-dimensional waveguide arrays. So the main particular property of these systems is that we're going to look at situations where we have individual waveguide modes of a dipolar structure, and essentially in the condensed matter context that correspond to having modes which originate from p-bands. If we look, essentially we will have for the uncoupled waveguides, we will have two orthogonal degenerate modes, and I will call them psi A and psi B. So just in this case we have horizontal dipole moments, and this one will work with dipole moment. So the question then is, if we have these kinds of systems, what kind of nonlinear localized modes? We will call them discrete solitons. Gap solitons is another word which is often used in this context. So depending on what kind of lattice types we have, we are going to look particularly in square lattices and triangular lattices, what kind of these structures we will have. And then, okay, my third apology here is that this talk was originally prepared for an audience with more optical backgrounds. So if there are some things that you think are unclear, I should explain more. I would be very welcome if you ask questions through the talk. So please, anything that is unclear, just interrupt me. Okay. So maybe I should say a little bit, because I didn't include here a picture of the geometry really. So what we are looking at is what we call spatial solitons in this kind of waveguide structure. So essentially, what we have is a three-dimensional structure where we have transversal x and y directions, and then we have a longitudinal z directions where the waveguides are extending. We are going to look at situations where we have stationary solutions. So essentially, we have no time dependence in the problem, but what we do have is, as we will see later, that we will have equations where the longitudinal coordinate, the z coordinate in this notation, will play like the classical role of time coordinate in a Schrödinger type picture. So if you think about Grossbit-Ajewski type models, for instance, then you have a time derivative. Here we have a set derivative which plays the same role. So, but this will hopefully be seen also. Okay. So just some brief outline. So the idea is essentially to use a coupled mode type approach, which is similar to a tight binding approach in condensed matter, to derive some discrete equations for two coupled fields that describe degenerate waveguide modes of dipolar character. And the key feature that will be very important for the properties that we will see here is that we have an anisotropic dispersion, which means that even though we have a lattice which have rotational symmetry, the solutions will break this symmetry because of the anisotropy of the dispersion relation. And then we will use some rather standard techniques, some numerical analytical techniques for discrete nonlinear equation to describe strongly localized solutions and analyze stability and mobility of these solutions. I will just mention briefly how we discuss these features. I will discuss in the beginning here some recent experiments on these particular reduced symmetry gap solitons and second band vortex static solitons that was kind of making the motivation, the experimental motivation for this work. What we will see is that these kind of solutions can localize solutions that can be mobile in the lattice in certain directions, and we will see how we can obtain conditions for this directional mobility of these dipole modes. And how this vortex modes that we will observe we typically, in quite general situations, have oscillatory instabilities, and we will also see how we can obtain conditions for these instabilities. Then we will introduce a concept, maybe some of you are familiar with something called the Payas-Nabarro barrier in lattice models. I will discuss a little bit in the end about these concepts. So essentially what we will introduce here is something that we will call a rotational Payas-Nabarro barrier, which essentially quantifies the minimum energy you need for rotating a dipole mode in the lattice. And as I mentioned, so of course there are people here who have been studying very similar models, but in a completely different context. So this was Yanni's work that I found, and I was very happy to see this paper published earlier this year. So essentially, you may describe these quantum states of p-band bosons in optical lattices in a mean-fit model, describing a superfluid regime with very similar types of equations that we will derive here. So also Yanni told me that there are some earlier references also that I was not aware of in this context. Okay. So some of the experimental motivations. Let's start with what was sort of the direct experimental work that motivated our first studies in this context. So this was a paper that appeared in 2006 in PRL, where people look at the so essentially what the kind of optical structures that we are considering are what are called the optical induced lattices. So it means that essentially you have you create the waveguide by guiding wave, by guiding light waves. So essentially you have some kind of photorefractive material, but by shining light, you create a waveguide structure. So here is essentially the waveguide structure, the periodic potential that you create by light. And then you may use this optically induced potential to trap an additional light beam, and this may then cause this kind of localized nonlinear modes that are illustrated in these pictures here. So what is particular with this kind of modes that were created in this experiment is that what is rather well known from previous studies are the properties of these discrete gap solitons that originate from the first band. So this will sort of correspond to just the symmetric S-band modes. But essentially you may also get localized structures that originate from the band edge of the second band. So essentially, you have the band gap. You have a band gap structure here. So here is the ordinary johansson picture. So this is the x point. So in this case, you have the x point corresponds to pi over d in the x direction and the 0 in the y direction. So essentially, if you look at the dispersion around this point, of course, you do see that typically it's anisotropic. So it means that since these localized modes essentially are the extent, the spatial extent of these localized modes essentially are connected to the dispersion, to the curvature of the dispersion relation. What you will see is that typically you will get modes that break the symmetry, so you get the mode. So here is one lattice direction, a mode which is very extended in one lattice direction and which is very, very localized in the other lattice direction. So this is a typical modes that you can get originating from these structures. So if you look at the phase, so here is the amplitude and the phase of this of the band edge mode here, and of course you see that you have the pi phase shift here showing that you have a this type of structure. So what's interesting is with this kind of modes is that if you tilt the lattice, you may cause a mobility of this these modes, and essentially it's mobile along the direction where it's extended. So essentially this behaves like a continuum soliton more or less in this direction. So you may move it in this direction, but on the other hand, it is very, very immobile in that direction. So we have this property that is called directional mobility of these discrete solitons. That are caused essentially by the anisotropic nature of this space. Then this essentially the same thing was extended to a triangular lattice. Okay, I don't think I need to say so much more about this, but essentially you have, of course, also in this case you have a dispersion relation which contains points corresponding to the band edge of the second band, and also here you may derive this. You may find experimentally these kind of localized modes essentially having these dipolar structures. So here is one unit cell, and you see you have the dipolar structure within this unit cell. Essentially, some spreading outside these modes, but essentially it's mainly localized in one unit cell. Then there was independently another group by Motisegev in Technion, I think, and he is so they essentially looked at the similar problem again, a square lattice. So what they did was that instead of exciting just single dipole mode, you take essentially a linear combination of a band edge mode in the x direction and in the orthogonal x prime direction, and you take this phase shift and with a factor pi over 2. And so what we create then is that you get the band edge mode, which essentially corresponds to this kind of array of counter-rotating vortices. So then when you turn up the amplitude on the light beam, you will, due to the kernel linearity of the system, you will get these structures localized, and essentially you will see this second band, what they call second band vortex solitons that essentially corresponds to, so this is an amplitude picture and this is a phase picture, which essentially corresponds to a vortex, which is, you have a localized vortex essentially in one unit cell, and then you have sort of, well, the remainder of the other cells here are essentially, you get an exponential localization essentially. The phase picture is not so clear here, but I guess if you really try, you can see that you have a 2-pi rotation in one unit cell approximately. Okay, so this was essentially the experiments that motivated our study. And of course, we were not the first who were considering these kinds of modes. So as far as I know, the first prediction was obtained already in the mid-90s by Sajid John and Akespek, the two papers, 93 and 98, where essentially they use an approximation of slowly varying envelopes. So it means that essentially you look at some continuum-like equations. You assume that you have a smooth envelope, so you can do essentially a continuum continuum modeling, which you can do if you're close to the linear band, if you have small amplitude of the solution. So essentially, you sort of treat the discreteness just as a weak perturbation of the system. So
what do you mean with the linear band?
Okay, so the linear band is essentially the linear dispersion band. So this is essentially the linear band. So if you have a small nonlinearity, it means that your solutions will only go close to the bifurcation point here. They will only go a little bit outside, out in the gap, and that means that the envelope will still be reasonably smooth. You will still have something which can be modeled by a continuum equation with a good approximation. But what we will see is that when you go out more, when you increase the amplitude, you will go out more in the gap. You will get stronger localization, and then you cannot anymore describe the system with a continuum model. So this is essentially, for instance, a structure like this here. You could get a good continuum approximation in this direction, but you have no continuum like behavior in this direction. It's more or less localized in one lattice row. Okay. Yes. So this was essentially the kind of picture that they obtained for these solutions. So essentially you have this one dimension here. We still have sort of continuum approximation. Then the prediction by the group of Motisega, they made a theoretical paper before their experimental paper where they predicted these second band vortex lattice solitons. So essentially this was the sort of the theoretical prediction of the vortex that I showed you in the previous slide. Then more recently, actually, after we initiated this work, there were a couple of other papers by Shi and Yang, where they did numerical continuation. So starting essentially from the linear band edge, they make a numerical continuation of solutions and see that actually they do survive, and you get different families of solitary waves, not necessarily with a smooth envelope. And there was also a bit later by Kalinovsky and other people a rigorous proof that these localized gap solitons, that indeed they do persist beyond the small amplitude limits. There were some special conditions of the potential that should be separated in this paper, but I think they extended it. So there was sort of the knowledge that these solutions that were found originally here, that they could be also continued beyond this limit, but the properties were not known in detail before. Okay, so the approach that we use then is to consider essentially a system which is strongly discrete, and we will use the coupled mode theory, which essentially is a standard technique in nonlinear optics, and it's very, very similar to type binding approaches in convex matter theory. So essentially what you do is that you start, assume that you have a single two-dimensional waveguide. So the assumption now is that we should have two orthogonal modes with the same propagation constant, k, in this case. So the propagation constant here is then the wave number in the longitudinal of the Z direction of the wavelengths. Assuming then that you have for just for an individual waveguide, you have just the V here is just the single site, the potential for a single waveguide, and you have just the ordinary equation for the modes. And if you now assume that you have a lattice of coupled waveguides, so essentially you have a lattice, so at each site n, xm, ym, you have this potential. So what you do is that you express the total field as a sum of individual waveguide modes. So am is then the coefficient of the psi a, and bm is the coefficient of the psi b. And do what is essentially corresponding to the type binding approximation. You assume that the modes are weakly overlapping. So essentially with perturbation theory you can derive this general set of coupled mode equations where you have...
Should there be an index m also in the field psi a? Or
No, okay.
Where is the index in?
So essentially, essentially you have a mode at each site. So the modes are essentially corresponding to your Wannier functions, for instance.
But then it's depending on the site, right? And
well, essentially you have an x-y dependence here. So of course the x and y, when you look at the that is of course you write x is equal to n times a, or y equal to n times a, etc. So the index is sort of included in the x, y.
But you have so it's just shifted to this. So you could have x minus xm or something.
Yes.
Okay.
Right. But the important thing is each mode is sitting in a single layer, and the modes don't change. But they are assumed to not change. The perturbation is assumed to be sufficiently weak so that we can do the expansion in individual waveforms. So the general set of equations that you will get is essentially you get two coupled equations for the A and the B coefficients. So you have coupling coefficients that couples on the different sides, couple the CAA, couple the A modes, CAB, couple cross coupling between the A and the B. You have a nonlinear term. We assume a curve nonlinearity, a cubic nonlinearity in this case. And you have also, when you get this nonlinear cross coupling terms, essentially due to the interaction between the modes at a single waveguide. So these are essentially the kind of standard general equations that we derive. The corresponding one for B modes. So essentially, you have the nonlinear parameters gamma and sigma, which are essentially determined by the geometry of the waveguides and the strength of the nonlinearity. And then we have the coupling constant C, whose detailed structure are determined by the geometry of the lattice. So in general, the notation here is essentially that CAA is a coupling between. So A modes, remember, A modes will always be horizontal, and B modes will always be vertical. So CAA will be coupling between horizontal modes, and B would be coupling between vertical modes, and AB would be cross coupling. So these two will always be equal, as you can see. So they are essentially just overlapping because between these modes.
Short comment also, actually, I mean, you said that these are similar to this p-band in field theory, and it's true, and it's actually similar also to the spinor condensate formula. So, I mean, what people do in spinor condensate in the mean field level, I mean, also the equations there look similar.
They look similar.
And of course, the coefficients are probably, I mean, not different, but I mean, formally they look the same.
Also with the nonlinear, with this particular kind of nonlinear.
Yeah, I
that
think
looks
so.
like spin-spin interaction.
So it's a process is that, I mean, you would take two atoms of
Yes.
some hyperfine state, and they collide and they scatter into two others. And then they give rise to this sort of, I mean, at the mean field level, at this kind of terms.
Yes. Okay. I wasn't aware that it was precisely the same.
I mean, it might not be precisely
No, okay,
the same,
but
formally they look
yeah.
similar.
Okay, very good. So, very good for me to learn what people are doing in this field. As I said, I come from a different direction. Okay. So essentially, the approach now is to start with single waveguide. People are working with Hamiltonian lattice dynamics. We used to call this limit where we put all the coupling parameters to zero. The anti-continuous limit is sort of the opposite to the continuum limit, where you assume that you have smooth amplitudes. Here we have waveguides which are just behaving independently of each other. The simplest idea here is just to, we wish to describe solutions that are associated with the second dispersion band. So we just assume, okay, this is essentially showing the same thing just with different illustrations. But the psi A, as I said, will be horizontal dipoles, and the psi B are the vertical dipoles. Then, if you look at the fundamental types of stationary solutions for single waveguides, this is known, there are many early papers. A good reference book is the book by Kircher and Agrawal and the consultants. You can find a lot of reference in that book, essentially. So there are three fundamental types of stationary solutions, and the stability is essentially determined by the ratio of sigma divided by gamma. So sigma was the cross-coupling nonlinearity, and gamma was the self-coupling nonlinearity. So this was sigma, and we assume now that we have symmetric waveguides. In that case, the gamma the gamma for the A modes and the gamma for the B modes will be identical. So essentially, the critical parameter is the ratio between these two, sigma and gamma. The different kinds of modes that you may have is either the single mode corresponding to horizontal and vertical dipoles, where either the A or the B field is 0, and the other one has this simple form. And if you do a stability analysis, you will see that this one is stable, assuming that sigma over gamma is between 0 and 1 over 3. Then you have the second possibility that A can be either plus or minus B. That corresponds essentially you have equal much of horizontal and vertical, so essentially that's a diagonal dipole mode. So it has this form, and that one is stable if sigma over gamma is between 1 over 3 and 1. Essentially you do a linearization around this stationary solution, and you look for eigenvalues, and then you just check if the eigenvalues are real and complex, and then you find this. And the third type of modes, the vortex modes, where you have a phase shift with plus or minus I corresponding to vortices in clockwise or counterclockwise. And this essentially has this form. And for single waveguide, these are stable for all sigma over gamma between 0 and 1. So sigma over gamma will always be somewhere between 0 and 1. One can see quite easily from the detailed expression. Now, of course, you may have so the sigma over gamma parameter essentially is determined by the shape of the waveguides, and of course you have some very simple shapes, like if you have a circular waveguide. Of course, if you have a circular waveguide, then there is no difference between horizontal, vertical, or diagonal. All directions should be identical. So this case, in fact, corresponds to the marginal case where sigma over gamma is equal to 1 over 3. So in that case, we have marginal stability of okay. Now let's see what happens if you go away. You do what you call a continuation from the anti-continuous limit. So you look at waveguides that are weakly coupled. So there are essentially for similar but different systems called discrete vector solitons. There are some papers where people looked at similar effects, but not with this kind of degenerate dipole modes. So essentially, if we look, so we should specify the lattice. So let us first look at the square lattice. We assume for simplicity now that we take only nearest neighbor coupling. You may, and we did also include the next nearest neighbor coupling, but it makes some quantitative difference, but qualitatively, a weak next nearest neighbor coupling does not make any crucial differences. So what we get, essentially, we have. So let me see, M is the vertical and J is the horizontal direction. So we get coupling coefficients C1 and C2 here. So C1 essentially is the horizontal coupling between vertical modes, or the vertical coupling between horizontal modes. So these will be identical. And the C2 is the horizontal coupling between horizontal modes, or the vertical coupling between vertical modes. And notice the sign here. So this over that interval will be positive, while this one will be negative. So that's why I put explicitly a minus sign in front of here. So the parameters C1 and C2 here are positive. But in general, of course, this will be different since the modes themselves are anisotropic. So you will have the same coefficients will appear here, but the C1 and the C2 will be different. And that's what gives special properties. If you look at this dynamical system here, so again remember that the cell variable plays essentially the role of the time variable. Then you have two conserved quantities that are conserved now in Z, of course. You have the Hamiltonian, which is essentially the energy. So it's essentially this expression here with 4 Fodor terms in A and Bn. And you have also what is optically interpreted as the total power or the total norm. Of course, in a bosonic system, of course, this will be the total number of particles. So these are the two conserved quantities. And if you now do the numerical continuation, so typically what we do is that we start with a solution at this uncoupled limit. We slowly increase numerical decoupling, and we see using some Newton scheme to find new solutions, and hopefully get convergent solutions. And what we see, essentially, I'm not going through any details here. I just do a very brief summary of the main properties. So what we see essentially is that, first of all, that all these three fundamental single-site stationary solutions that I described may be continued smoothly for increasing coupling, and you may continue them all the way from the purely discrete limit to the continuum limit, so we can sort of cover all the path from modes localized at the single site to modes essentially described by pure continuum equations. So we have a smooth continuation for all these three types of solutions. And in the continuum limit, essentially, there are analytical expressions in terms of vector solutions, which is also essentially known. Can also be found in these expressions. So the linear stability, so essentially, again, I'm not going through any details. You get, if you have n Lattice sites, so essentially you have a real and imaginary part for each site, and you have two components, so A and B. So essentially, what it in the end boils down to is that you will get the 4n by 4n matrix to diagonals for an n site lattice. And if n is equal to 1, you can do it analytically, but when n gets bigger, it's a bit more tricky. You can do some perturbation theory for recoupling and essentially obtain some approximate analytical results for stability if you have strongly localized solutions. But in the general case, of course, you need to be okay, so for the results, then essentially, if you look at the case where sigma over gamma is not equal to 1 over 3, so you have waveguides which are non-circular, then essentially what you will see is that the dipole modes, the horizontal, vertical, and the diagonal one, essentially will keep the same stability properties as they did in the uncoupled limit. The vortex modes will be stable for weak coupling, but if we increase the coupling, we will see that we will get oscillatory instabilities of these modes, which essentially is due to the fact that you have a resonance between a localized internal mode and an extended mode corresponding to essentially linear extended lag oscillations. So we could obtain an analytical estimate for this instability threshold essentially by doing a perturbation interpretation of the stability eigenvalues for possible coupling. Then in addition, we should remember that if you have a two-dimensional system, a two-dimensional continuum system with a cubic nonlinearity, in fact, you always have what we call Vachito-Kolokolo, essentially collapse or quasi-collapse instability if for this kind of systems. So this is essentially well known, and there are sort of rigorous proofs of that for continuum systems, two-dimensional systems, cubic nonlinearity, the solutions will always be unstable. So essentially, what you will get is that the solution will collapse, and this collapse, well, of course, the collapse will not go on forever. You will reach some point where this continuum approximation will break down, and then you will see that you will get some trapping on some single site typically in as an outcome. But this we see for all. So that kind of puts some perspective also on the earlier solutions that use the continuum limit, because if you strictly work in the continuum limit here, essentially everything we find is unstable. But of course for the real system, things are stable because we have the discrete, the regular stabilizers.
You looked at which states are stable at which parameter regimes. I mean, did you look at which is energetically the lowest one? I mean, these vortex modes, I mean, they were stable at some regime, I think. I mean, were they like the lowest energy modes?
No, they cannot be the lowest energy modes, because if they would be the lowest energy modes, they would be stable. So the vortex modes could possibly be at the points where they are stable. They could possibly. Okay, no. The answer is no. We did not compare, as far as I remember. But of course it's an easy exercise to plug in these expressions in the Hamiltonian here and check which has the lowest one. But as far as I can remember, we did not check the vortex mode I believe that the vortex mode is always has higher energy than the other mode, but I think we did not check it carefully. Okay. So in the maybe more interesting case where sigma over gamma is equal to 1 over 3, we have the circular waveguides, and then of course we had marginal stability of all modes for a single waveguide, and then what we find is that the horizontal vertical dipole modes will be stable, and the diagonal modes will be unstable as soon as you increase the coupling constants when you have this anisotropic modulus. So essentially what you get is that you get, I guess, a physically reasonable result that you get favorable dipole orientations that are essentially selected by the lattice directions. So the dipole will align themselves essentially in the direction of the lattice. So this is what you will see for the stable modes. Of course, the other modes will still exist as solutions, but they will be unstable. And what you will see for the vortex modes is that, in fact, they will develop very weak oscillatory instabilities. In principle, if you have an infinite lattice, we will see that for any values of the coupling, you will get weak oscillatory instabilities. So this is a kind of interesting phenomena. So you have very strong finite size effects in these properties. So this picture essentially shows the real part and the imaginary part of the eigenfrequencies of the vortex modes. So imaginary, as soon as you have an imaginary part, it means that you are unstable. So the lines here are essentially the extended, the phonon type modes in the system, while this parabola here is essentially the internal mode that is corresponding to an internal oscillation in the vortex. So essentially, as soon as you have a collision between two eigenfrequencies here, between this internal mode and these extended modes, you will create a resonance. But if you have a finite system, your phonon band is not continuous, you have discrete eigenvalues, so you will see this discrete set of resonances. But as you increase the number of sites in the lattice, you will get more and more of this resonance, and essentially you will sort of get more and more narrow instabilities here. And in the end, if you go to the continuum, so to the infinite size limit, where the phonon band is continuous, essentially you will get some curve that essentially gives a smooth curve. So you will typically very weak instabilities for small coupling, but when you increase, essentially you will get strong instabilities. So this is essentially an effect that comes due to this resonance. Okay. Only in the case where the coupling constants are equal, you will get marginal stability of particles. And you will have this instability, positive axis stability. Okay, so some words about this directional mobility that I mentioned in the beginning. So in fact, if you look at the single horizontal vertical mode, essentially that you will have either A or B will be 0, and then in fact your equation here will be very simple. Because if B is 0, then this term will disappear here. So then essentially you have just an equation for one field. So essentially you get back just an anisotropic discrete version of the non-Schrödinger equation, and that one has essentially been studied before in several papers. So then it was actually known from previous results that such solutions will be stable. And mobile in the strong coupling direction if you have sufficiently strong anisotropy. So they found that essentially if C2 over C1 here, the relation is more than 0.17, you will get these solutions that may move as this reduced symmetry discrete solitons that I showed in the experimental picture. So essentially you have this treatment of stability. Don't bother about this parameter here, it's from a different paper, it's something that essentially you have this stable version for strong anisotropy. For vortices, on the other hand, you don't get any stable mobile solutions, which essentially is due to the fact that you never get. Since the vortex is a symmetric combination of the A and B modes, essentially you never get this directional property of these vortices. So for this phenomenon, that's not the case. Okay, well, I'll try to not be too much detail here, but just discuss a little bit about the results we obtained for triangular lattice. There are many, at least a few previous papers working on one component, triangular lattice, discrete sorters and waters, etc. Essentially, well, you would have, depending on, so the triangular lattice, essentially, we use the J and M here in this direction, so we have the J is essentially going in this direction, and the M is essentially going it's going downwards actually in this direction. So then, of course, again, the A are the horizontal dipole modes, the B are the vertical dipole modes. And then, of course, now you have couplings not only in the horizontal direction, but of course you have couplings also in the diagonal directions. We introduced this CAA corresponding to couplings, diagonal couplings between A modes, the CAB corresponding to diagonal couplings between A and B modes. Notice that if it's negative in this direction, it could be positive in that direction. And you have the CBB, which essentially is the coupling. So again, we put an explicit sign here, from the physical properties of the modes here, you can see that the C1, this one is positive, the C2 here is positive, the CAB, this one is also positive. But the sign of this CAA and CBB, sorry, these two, we put them with the minus sign here, but essentially it depends on the particular geometry. So in principle, it depends on how the detail of how these modes actually look, so they might be either positive or negative. I will not. So you see, I mean, you get really very many parameter system of equations here, and we didn't want to sort of spend too much time on looking at all these different parameter dependence. So because there are also things to do here, but we look simply at the simplest situation where we have circular waveguides. So essentially, we choose a particular value of sigma gamma over gamma is equal to 1 over 3. And then, in fact, one can say that due to the symmetry properties here, you will get particular relations between the coefficients. So essentially, you can express the CAA, these diagonal couplings, in terms of the horizontal and vertical couplings. Essentially, you can do this as soon as you have waveguides which have the same rotational symmetry as the lattice or higher, of course. So as soon as you have at least 6-fold rotational symmetry of the lattice, you will have these of the waveguides. Sorry. You will have this relation. As a parenthesis, this kind of model was in fact known again in completely different physical context. I learned that people in plasma physics are studying this kind of models as a model for dusty plasma crystals, and again you have this hexagonal, where you typically create this hexagonal matrices, and again you get a model which looks very similar. So that there is a lot of applications in different systems. Okay, so what you will see here is that you have 3 classes of distinct fundamental solutions that appear from the anti-continuous limit. So when you turn on the coupling, so either you can have dipoles pointing in a lattice direction. So here I put the case where you have a horizontal dipole, so this means that B is equal to 0, you have only the A component here. So it turns out that when C2 is bigger than C1, so C2 was essentially the coupling between vertical horizontal modes in the horizontal direction. So when this one is bigger, then these ones will be stable. So this of course is also physical, yes, because then you have a stronger coupling in the lattice direction. So again, the lattice direction is favored single out the status difference. On the other hand, you may have solutions that are pointing between lattice directions. Of course, when you're pointing between, of course, you can choose it like here to be vertical. Of course, you could also put it with any 60-degree rotation here. So the first one will of course be the one which is just 30-degree rotation. So these modes are stable when C2 is smaller than C1. So in that case, you have the favorable situation that the coupling, this coupling will be stronger. Again, you have this colloquial quasi-collapse instability close to and the vortex modes again will be plus minus I times the A field. They are always weakly oscillatory unstable. Just some parentheses here that if you put C2 equal to C1, in fact, you get these modes will be stable depending on the nonlinearity, whether it's positive or negative, focusing or defocusing nonlinearity. This one or that one, this one is stable in one case, and the other one is stable in the other case. It's a quite funny behavior for those of you who are interested in some funny power laws that the stability here behaves as a Chapman concept to the power of certain over 2, which is quite unusual power law. We didn't really find it analytical. We found it okay, so how about mobility in the triangular lattice? Well, in fact, if you look at the parameter relations here, so if you put some specific relations, parameter relations, if you put, for instance, C2 is equal to C1 over 3, then you will see that if C2 is equal to C1 over 3, then this coupling constant here will be 0. So essentially you isolate different planes in the lattice. So it means that in this case, essentially you have effectively a one-dimensional situation. So you have also the opposite when C2 is equal to 3C1, and then the other one, another one will be 0. So essentially, you have some particular values where you, in fact, when you go to large coupling, you in fact you get a truly one-dimensional structure, and essentially you get a solution which is perfectly mobile in this direction, but completely immobile in the other directions. But these are, of course, very particular parameter values. But also, if you're close to these parameter values, you may get a reasonably good mobility. Okay, so what I will end with is essentially to discuss these properties of some quantification of the properties of translational and rotational mobility of dipole modes. So what I mentioned in the beginning was this so-called Pius-Navarro barrier, which essentially is an old concept in solid-state physics, essentially in terms of motion of dislocations described by King's of lattice equations. For discrete modes, this was, I think, for the first time discussed by Kirchhoff and Campbell in 93. So if you look at the energy difference between, let's say, a mode that is centered at one side and compared to a corresponding mode that is centered at two sides. So essentially, if you would like to move this mode, you would like to slide it in this direction, so you should sort of somehow go from configuration like that to a configuration like that. And of course, if there is a barrier, an energy barrier between these two modes, well, the bigger barrier you have, the more difficult it should be to move it. So essentially, they define this Pius-Navarro potential barrier as the energy difference at fixed power, because remember that power is a Poisson quantity between these two modes. So that sort of gives you an estimate of the possibility to move these solutions. Now, of course, we have dipole modes that are pointing in certain directions, and of course, we can also calculate what we call a rotational Pius-Navarro barrier. Which is essentially then is the energy difference between the stable and unstable dipole modes, again, at fixed power. So of course the stable dipole mode will have lower energy than the unstable mode. So then this energy difference should then correspond to the minimum energy needed for rotation of these stable dipole modes. So let me just show you some pictures. So essentially, so here's for a square lattice. So the stable mode in this case, it's for quite strong anisotropy, 0.15 for circular waveguides. So here's the translational Pius-Navarro barrier, the red curve, and the rotational, the blue curve as a function of the power. So the translational barrier, we take the difference between the one-side stable mode. So here's the in this case it's a vertical mode we chose. So here essentially is the absolute value of the B field, the A field is 0. And if we slide it in the easy sliding direction, then we will have the two-side mode. So here is the unstable two-side vertical mode. So we calculate the energy difference between these two. So we get translation, the red curve here. And if we calculate the energy difference between, so these again, if it was the stable one-side vertical mode, and here we have the unstable diagonal mode. So here we have an A field and a B field with the same component essentially. So you calculate the energy difference of these two, you get the rotational barrier, and you get the U curve. So the general picture then is that when you increase the power, translational barrier increases, which essentially is a familiar property because when you increase the power, the solutions will be more localized, so it will be more difficult to move them. While the rotational barrier will decrease, which essentially also you can understand because you will approach more and more the single-side solution, and the single-side solution essentially you should essentially get the value which goes to 0. So this should be. So here's just some general pictures. So yellow here is small value, and it's translation and rotational. So this is what shows that translation value is typically very big. When we increase the C2 over C1, so here's just for strong anisotropy. For strong anisotropy, you have the situation where you may get good mobility, in translational direction, but when you increase the anisotropy, essentially you have no mobility for the rotational barrier. So here's a dynamical illustration of this rotational barrier. So essentially you take a stable one-side vertical mode, you put the perturbation. So in this case you start with a mode which is purely in the B component, so essentially your A and K is 0 in this particular situation here. So then you perturb it, and essentially you perturb it by essentially kicking it. So you give it an imaginary part. If the mode is real from the beginning, you give it an imaginary part. So this is a normal power conserving perturbation. So you see very clearly this threshold that if you just kick it a little bit, so here's the initial, you see that this is the intensity at the central site. So here you have the A component, and here you have the B component and the A component. So from the beginning you have just B, and then you get some oscillations, but you never exceed this barrier. So you still have the main. You always have the main part of the B component. You have a diagonal solution here where A to B acting as the barrier. So essentially here you have the same thing when you just get Ballard threshold. So essentially here you start to get the exchange between A and B. So it's really rotating. Similar thing for triangular lattice. So here is, remember that we had good translation mobility when we were close to this value 1 over 3, C2 over C1. So here is, I chose 0.35. So here we have a translational barrier which is, at least for small power, reasonably small. So you have essentially, you have logarithmic scale here, just to illustrate this feature. So here you have essentially a crossing point here, where rotational barrier becomes more than translational goes very, very quickly. So here are the modes essentially that we used to calculate these properties. And the general picture essentially what you see here is that when you are close to this value 1 over 3, translational barrier becomes smaller than otherwise it's and also some dynamical illustration of the rotational barrier for triangular lattice. Okay. So same perturbation again. You start with something which is just in the B, in the vertical part. Small perturbation, nothing happens. B perturbation starts with. Notice that in this case, of course, you start with a solution that is, in this case, pointing in the vertical direction. But of course, the first unstable mode is the one that is pointing 30 degrees. So that one essentially is the solution which has the relation B squared is equal to 3A squared. So essentially, this is why you get the barrier here and not in the middle. So here, it starts to overcomes this solution, and somehow here, you see, it slows down here at the barrier, and then it speeds up. So here you have the next stationary solution here, the next stable solution sort of in the next lattice direction, and then plus around here. So the last slide I have here is just an illustration that you also may have a reasonably good translational mobility for the triangle lattice. So here you take stable one-side vertical mode, and the perturbation in this case to get this one to move, you should put essentially a phase gradient in the direction, in the EC mobility direction. So essentially you multiply each component here with, for instance, you may do this in different ways, but the simplest way is just to multiply this with a factor e to minus I epsilon j, where j is the direction where you have the EC mobility. So you see that, okay, so these are the central side and the two horizontal neighbors. So if you just put a small perturbation, you see you just get some small oscillations. If you put a bigger perturbation, you see that you start to get mobilities here with one side and two sides. Mobility is not very good here. You have a lot of additional oscillations that this gets happening. So I just want to end with showing some additional simulations. And let me see if I can find this here. Let me see. Okay, so essentially, what I should say something before I show it. Let me restart it. Where it is here? No? Okay. So essentially, these are simulations looking backward done by my collaborator Andrei Sokurko for essentially the model, the original model, not the discrete model, but the model with the full continuum model with the periodic potential, essentially the periodic potential that corresponded to the experiments that they did. So what was the starting point here? If we restart it, so essentially here it's a dipole mode. You start originally with a dipole mode oriented along one lattice direction. So then it's given this kind of kick that I described before. So here's a square lattice, and you kick it in this direction, and what you see essentially is that indeed it starts to rotate. So for instance, if you stop it here, you have the D mode. Sorry, the diagonal mode, where A and B components are equal. And then you run it a little bit more, and then you see, okay, here again, it's back with the same shape as before, but 90 degree rotated. And then it can go on like this. So here again, you have a new diagonal mode, etc. And then it can go on for quite some time. So you see that this rotational is really something that we not only find in discrete equations, but really takes place also if you do the simulation for the more realistic model.
So those two central blobs are within one side?
Yes. Precisely. So I should say that this is the intensity. So essentially, this is the node here in the middle. So here's the dipole. So here's this is the positive, and here's the negative. So this is here's one unit cell, and here you have the next one. And final picture, the corresponding or a similar one for a triangle, and this one is a little bit tricky, and I'm not sure I understand myself what this one is doing, but let us see. So here, here you see the triangle. That is again here is one unit cell, essentially one waveguide. So you have you start essentially with the vertical dipole mode in this case. So this is in fact for the situation where the vertical mode is unstable and the one 60 degree rotate. No, sorry, the 30 degree rotated version is stable. So you start with this one, which is unstable, and what it does is essentially that it after some internal dynamics, it reshapes itself to the mode that comes in the diagonal direction. So in this case, okay, you should be a little bit more tricky with the perturbation. I think in this case to really get it rotated, because this one actually stops here. But saw from the discrete equations essentially is that we should be able to also so here we can positive negative. Okay. So I just want to end with the beginning. So what we did essentially was that we looked at this couple model approach to describe discrete equations for these two couple fields, describing general equations, most of that polar character, and we saw that due to this anisotropic dispersion, we had many features that are not will not appear for, let's say, the more standard discrete solitons that people have been looking at for many years by now, and we have in particular this directional mobility created this reduced symmetry gap solitons, and this vortex second band vortex lattice solitons that are localized essentially within one unit cell. I think the main new, let's say, conceptual new thing that we introduced here was this concept of rotational Tyson-Dollar band, showing how we could quantify this sort of ability for a dipole model object. And I would be very, very happy to see if some of these contexts could be used also in this context of P-band model process. So it would be very interesting. Thank you.
Questions?
Have many questions. So this 1/3, is it an exact result for these cylindrical waveguides, or because for us we find it only in the Gaussian approximation?
Wait, one moment. The one
Sigma over gamma.
Okay. This one fell because there was another one. Yes. Let me see. Just so we are sure about what we're talking about. No.
But isn't sigma over gamma?
We are talking about this one. One third is the one we're talking about. This. It is an exact result, assuming that you have that you have a waveguide which is circular.
But if you would you derive it from single particle model, or if you take interaction into account? So let me see. I have to. Yes. The assumption is that you have essentially you have a mode. You have an individual waveguide mode. That it is the. Let me see. It was 4 years ago since I actually did the calculations.
I guess these functions psi A are somehow computed in a single waveguide.
Yes, precisely.
Without having these other waveguides around.
Yeah. So everything is sort of assumes that your mode is not, your individual mode is not disturbed by the lattice. So this is sort of the basic assumption that your individual waveguide mode are the eigenmodes of the circular symmetric waveguides, and then this will be 1/3.
Yeah.
But of course, if you sort of go to higher order, of course the fact that you have a lattice, of course, affects also the waveguides, the waveguide modes, and then I suppose then I guess you will get some corrections to these values to higher order.
So then it's like in our case.
I assume so. Yes, because it's essentially that is the basic sort of approximation of the couple mode theory, that you assume that you can do all the expansions using the modes of the individual waveguides, the uncoupled waveguides. Yeah. So the corrections will sort of come in next order.
And this PM barrier, I've only seen it when you discuss solitons in the discrete nonlinear Schrödinger equation. And I discussed with some colleagues, when you look at vortices, And depending on how you rotate your lattice, you should have a p-n barrier there as well. Is it something I haven't seen it in cold atoms, but is it something you have seen in your field? So if you rotate your lattice around a point where the lattice is maximum or where it's minimum, it should give a sort of p-n barrier there as well.
So let me see. What would you compare?
The energy of your vortex state if you rotate your lattice around.
Okay. So if you have vortex either centered at the lattice size or centered between lattice size, so you should move you would have to move the vortex.
Yeah.
Yes. Of course, that is something that you could define. Of course, the question is if it makes any physical meaning. Because I mean, to make a physical meaning of this concept, you need to have essentially you would need to have a continuous family of solutions that sort of takes you from the vortex that is centered at the side to the one that is centered between the sides. So of course you can always take these two solutions and compare the energy. But the question is it at all possible to move it?
But you can, I guess, if you rotate the lattice, you will fix the middle point of rotation. If it sits on a maximum or on a minimum.
Yes, but is it possible to move the solution from the maximum to the minimum without destroying it?
But also the stability of if you're sitting on the maximum or minimum depends. It's different, at least for solitons.
Mm-hmm.
So maybe one is more stable than the other as well.
Yes, the problem typically with discrete vortices are that they are purely discrete objects. So I mean, they don't have sort of something like close to continuum approximation. Essentially, I mean, the reason why it makes sense here to talk about this Peierls-Navarro barrier is that you do have one direction where you have a smooth envelope. So essentially, you have a direction where you do have something which is close to continuum approximation, where you can move it.
Okay.
But if you have a purely a very very strong system, like if you would try, it would be the same thing as saying that okay, I could also compare the solution between the in the other direction. I mean, instead of going in the smooth direction, I could also compare the Hamiltonian in the very very strongly localized direction. That would also give me something like a Peierls-Navarro barrier. I mean, conceptually, it would give a Peierls-Navarro barrier, but it wouldn't make any sense physically because there is no way that I can make this solution sort of move in the transverse direction. So the question, and that's a general problem with discrete vortices, that at least in the models that I have been looking at, they are immobile. So even if you can define these two different vortex classes, I mean there is no way to with some simple perturbation just make the vortex move from one to another.
Yeah, I think my point is that the p-n barrier is related to mobility, but it's also related to stability.
Yes, it is also because you compare the energy at a fixed one norm or particle number or whatever. And of course, what you know is of course that the one with the real ground state of course should be stable. So the one that really has the lowest energy should always be the stable one. Then of course the other one might also be stable. That you don't know, but what you should know is that one of them should be stable.
No questions?
Yeah.
Well, maybe you can continue during the lunch break. I think this might continue forever. So let's thank the speaker again and thank you.